So for EAS, activators and deactivators, or substituents that act as deactivators and activators. At the far end of the spectrum, the most powerful activating agent is an NR2. And the reason why is because of this lone pair that it has that makes it really good at resonance stabilizing. Next to that would be the OR group. And that's pretty much the end of the activators. If I had a purple color, I would make these two purple. But I'll go ahead and just relabel each and every one of these as either an activator or a deactivator just to drive home that point. So NR2, activator. OR, activator. NHCOR, that's an activator. Alkyl groups are activators. Hydrogens are completely neutral. They're neither activating nor are they deactivating, but everything else other than that, everything south of the border, as they say, so the halogens, these are all deactivators. Cyano groups are deactivating. SO3Hs are deactivating. R2s are deactivating. And of course, NO2 is deactivating. And we'll try to explain, I'll try to explain that to you guys, I guess in depth on later videos when we start talking about carboxylic acid chemistry and things like that. But if I were to just take an imaginary line between the halogens and anything really with a carbonyl group attached to it, imagining that imaginary line, and then go ahead and just make a right, all of that there, and a left, all of that there. Really driving home that that's the divide. The divide is between the halogen and anything with the carbonyls. Everything over here, these tend to be, and these are, I'm not saying that reactions with this do this. I'm saying that if you have one of these as a substituent in your benzene ring, then you try to do a Friedel-Crafts or whatever, some type of EAS, electrophilic aromatic substitution reaction, you're going to get usually a meta substitution. Meta is always 1 and 3 for the substituents. And what's interesting about this is that you can have no Friedel-Crafts reaction going in on everything, and just to reiterate this, everything that is to the left of that imaginary line I put, none of these guys can do Friedel-Crafts. So even though halogen are deactivators, they can still do Friedel-Crafts reactions. So anything north of this imaginary line that I've drawn here, these tend to be ortho and para directors. Remember, ortho 1 and 2, para being 1 and 4, and they can do Friedel-Crafts reagents, except for NR2. For whatever reason, this cannot do, this has no Friedel-Crafts reactions. And perhaps someone smarter than me can explain this. They're saying that it's too activated. This is what my book, the point that my book kind of drives home, is that if you have, say, a halogen already as a substituent already in your benzene compound, so I'm just going to put that NR2 there, NR2, and you try to do a Friedel-Crafts reaction, I'll make sure I draw those lone pairs. And so whenever the aluminum tetrachloride comes in, that this will, before the say for example, well, not necessarily for Friedel-Crafts, but remember there's a halogen attached to either a acetyl group or either to a alkyl group, but that it will do this reaction beforehand. But I'm confused by this, because what the book says, or at least what my book says, is that because this is a Lewis base, this is going to react with this, that this is an acid. Every reaction is done under acidic conditions. Every single reaction that I just talked about is done under acidic conditions. Why is it just Friedel-Crafts that it'll react with this? Structurally, I don't see the difference between, I mean, obviously this is a little bit different, but it's, at the end of the day, this is a Lewis acid. I don't know. I still haven't understood that. But for the purposes of this course, NR2, no Friedel-Crafts. All these guys here, to the left of the halogens, no Friedel-Crafts, and they're always meta directors. And we'll go into more detail on this with carboxylic acids.